What specific problem does the SVP algorithm aim to solve regarding vision language models, VLMs, and what are the limitations of existing approaches that it seeks to address?
The SVP algorithm aims to solve the problem of misalignment between visual and linguistic modalities in vision language models, VLMs, specifically addressing issues of hallucinations and biases that lead to generated text that does not accurately reflect the visual content. Existing approaches, such as fine-tuning with supervised data, are costly and sample inefficient, requiring extensive image-text annotations. Preference-based post-training methods also necessitate curated preference pairs, while test time methods are limited by their computational demands and model-specific heuristics. SVP seeks to overcome these limitations by leveraging external feedback from a small grounding model to enhance alignment without the need for costly annotations or preference data. This innovative approach allows for improved grounding and self-improvement in VLMs, making it more efficient and broadly applicable across various frameworks.
How does the proposed SVP algorithm work? Illustrate its methodology step by step, including the role of each phase in the overall process.
The proposed supervision-free visual projection (SVP) algorithm operates through a three-phase process: inner loop sampling, scoring, and outer loop adaptation. 1. Inner loop sampling. In this phase, a base vision language model (VLM) generates detailed image descriptions for a set of input images. These descriptions are then processed by a small pre-trained grounding model, which extracts spatially enriched grounding outputs, providing feedback that conditions the VLM to produce text tokens that better align with the visual information. 2. Scoring. This step involves employing a scoring mechanism to evaluate the generated samples based on their alignment with the visual input. The top scoring samples, which are deemed more informative and grounded, are selected for further processing. 3. Outer loop adaptation. In this final phase, the base VLM is fine-tuned using the filtered dataset of high-scoring samples. Importantly, the grounding information is not directly shown during this fine-tuning process, but is utilized during inference to enhance the model's performance on various tasks. Overall, SVP leverages self-improvement and grounding feedback to refine the alignment between visual and linguistic representations, significantly enhancing the VLM's capabilities without the need for extensive manual annotations.
Can you provide a simple yet illustrative example of how the SVP algorithm processes an image and generates a caption? Please detail the flow from input image to the final output.
The SVP algorithm processes an image and generates a caption through a structured three-step process. First, in the inner loop sampling, a base vision language model, VLM, generates multiple detailed image descriptions based on the input image and text prompt. These descriptions are then processed by a small pre-trained grounding model, which extracts spatially enriched grounding outputs, including noun phrases and corresponding bounding boxes, serving as feedback. Next, in the scoring phase, the algorithm employs a scoring mechanism to evaluate and rank these grounded samples, selecting the most informative ones that align well with the visual input. Finally, in the outer loop adaptation, the base VLM is fine-tuned using the top scoring samples, enhancing its performance without direct access to grounding information during this adaptation phase. This iterative process allows the model to improve its alignment between visual and linguistic representations, ultimately generating a more accurate and contextually relevant caption for the input image.
What are the theoretical and practical benefits of using SVP compared to other existing methods for improving vision-language alignment?
Theoretical benefits of using supervision-free visual projection, SVP, include its foundation on self-improvement and grounding feedback principles, which allow for enhanced alignment between visual and linguistic modalities without the need for extensive manual annotations or curated preference pairs. This model-agnostic approach enables SVP to be easily applicable across various vision language models, VLMs, addressing the limitations of existing methods that often require costly and sample-inefficient data. Practically, SVP demonstrates significant performance improvements across multiple vision language benchmarks, achieving nearly 20% enhancement in tasks like captioning and substantial gains in referring tasks, even for models with initially poor performance. Additionally, SVP effectively reduces hallucination rates and improves object recall, showcasing its ability to provide accurate and grounded outputs. Overall, SVP's innovative use of external feedback and iterative refinement positions it as a superior alternative to traditional fine-tuning and post-training methods.
How was the SVP method validated or tested in the experiments? Discuss the datasets used, benchmarks, and the performance metrics adopted.
The SVP method was validated through comprehensive experiments across 10 diverse vision language benchmarks, including tasks such as generative captioning, evaluated on COCO 2017 number caps and Flickr 30K, referring expression generation, RefCOCO, RefCOCO Plus, RefCOCO G, and visual question answering, Science QA, VQA V2, GQA. The performance metrics adopted included the CIDR score for captioning tasks, accuracy for visual question answering, and F1 accuracy and recall for hallucination and object recall assessments. The results demonstrated significant improvements, with SVP achieving nearly a 20% enhancement in captioning performance and notable gains in referring tasks, particularly for models with initially poor capabilities. Additionally, SVP's effectiveness was illustrated by its ability to reduce hallucination rates and improve object recall, showcasing its impact on the model's overall performance across various tasks and datasets. The evaluation also included comparisons against baseline models and other adaptation methods, reinforcing the robustness of SVP's approach.
What specific results were achieved using SVP across various tasks, and how do these results compare against baseline models? What insights do these results provide regarding the effectiveness of SVP?
Using the supervision-free visual projection (SVP) method, significant improvements were observed across various tasks and datasets. For instance, in captioning tasks, SVP achieved nearly a 20% improvement in performance, while in referring tasks it enhanced the model's capabilities threefold, particularly for models with initially poor performance. In terms of hallucination control, SVP increased the F1 score from 86.7% to 88.3% for a 7B model, matching the performance of much larger models. Additionally, object recall improved from approximately 79% to over 87% after 3 iterations of SVP. These results indicate that SVP effectively enhances vision language alignment, leading to better performance in generating accurate and contextually relevant outputs compared to baseline models, thereby validating the hypothesis that improved modality alignment is crucial for VLMs.